Inside a quantum computer, we exploit three fundamental principles of quantum mechanics: superposition, entanglement, and interference. So let's try to imagine what superposition looks like. You have a coin, and normally we can have heads or tails, but imagine I'm spinning the coin, and just picture it rotating. If I ask you, is it heads or tails right now? You would say, it's in a superposition of those two states. Only when I perform the measurement is it clear. Now, let's talk about entanglement. That is when it gets a little bit weird and very interesting, because imagine now you have two coins, and we rotate the coins, and they're both flipping. They're both in this superposition state. Each coin is independent. Whether this is head or tails has nothing to do whether this is head or tails. But it turns out that in my quantum world, I can get these two coins to behave in ways that have perfect correlation with one another. So I can create them in such a manner that when this is heads, this is always tails. Or when this is tails, this is always heads. The third principle is the principle of interference. And just like waves in the ocean, when they form a peak, we see the crest, and sometimes they can cancel each other, and we see the valley of the waves. I can do the same thing with my quantum bits inside the machine. So the way an algorithm works in a quantum computer is I put my qubits, my quantum bits, in a superposition, I entangle them in appropriate ways, and a set of operations, an algorithm, it's a set of manipulations of those qubits in such a way that I interfere them to get the right answer, and the things I don't want, they get canceled out. A normal question to ask is, what can you do with them? One is the original idea of Richard Feynman of go and build a quantum computer and use it to simulate nature. And we will be able to design and make calculations using quantum computers, new materials. Let's say we want to create a high temperature superconductor or a better fertilizer that is more efficient for the world. We will be able to use quantum computers for that. Then there is the whole category of mathematics. Somebody has worked out through theory that if you had a large enough quantum computer, you could have a proven advantage. Factoring is an example which has implications for security and cybersecurity. Grover's algorithm that has to do with search and the possibility to search faster databases. And then there's a whole realm of optimization and machine learning. Progress in optimization, which are known hard problems, you can apply to financial services. Portfolio optimization is a good example. And then you have the field of machine learning, where we have gotten accustomed to use neural networks on things like support vector machines to be able to encode information and perform classification. In 20 years, quantum computing will be so fundamental and important that it will have branched the field of computing itself, and to be able to impact almost every aspect of the service economy, because we would see implications also to artificial intelligence and machine learning. So I would say in 20 years we'll be in full bloom.